Hello, my name is Yazan Shnudi, and this is the video final exam for Engineering 305. For this presentation, I will be covering 10 topics that were covered in Engineering 305 while explaining each of them, giving an example, and showing how to do it in SAS JMP. Okay, let's get right to it. For our first topic, the ANOVA test. In the ANOVA test, the data is usually normally distributed. However, the proportion between groups follows an F distribution. We use the ANOVA test when we want to see if there is a statistically significant difference between the variances/means of 3 or more groups of data. It's similar to the t-test, but it results in less type 1 error, which is basically the rejection of a true null hypothesis. The difference is considered significant if it is less than 0.05, the p-value is. And for our types of ANOVA tests, we have the ANOVA, ANOVA 2, and MANOVA. An example of that is the ANOVA is when we have one independent variable. Example is like a type of ball like basketball, soccer ball, or baseball. ANOVA 2 is when we have multiple independent variables like the gender and major chosen of students at college. And the MANOVA, which is multiple ANOVA, is when we have dependent variables, usually more than one. Example is gas and the materials that go in it. For our ANOVA example, we use the data analgesics.jump, which shows different drugs, the person's gender, and how that affects how much pain they are feeling. We're going to be using a one-way ANOVA, and our null hypothesis is that both genders feel the same amount of pain, and the drugs do not affect how much pain they can feel. To conduct an ANOVA test in JMP, we have to go to Analyze, fit Y by X. For our Y response, we're going to use the pain index, and for our X factors, we're going to use the gender and the drug. Click OK. And then after that, we have to go to the red arrow right here and click Means ANOVA for the gender, and then Means ANOVA for the drug. If we scroll down, we can see that the p-value for our gender is less than 0.05, meaning that females and males feel pain differently. And for our drug, we can see that the drug affects how much pain males and females suffer from on different drugs. Another way we can use the ANOVA test is by analyzing fit Y by X. We would use the pain as our Y response, the drug as our X factor, and then we want to group them by gender. So if we go here, we click the Means ANOVA, we can see that females do not, that the drug used on females does not affect how much pain they feel. And now for our males, we can see that the drug used on males actually affects how much pain they feel, since the p-value is less than 0.05. For our second topic, we're going to be talking about the chi-square test. The data in a chi-square test follows the chi-square distribution. We use the chi-square test when we want to test for independence between two or more categorical data sets. So all the data sets we're going to use are categorical. The difference is significant if the p-value is less than 0.05, just like in ANOVA. And the XY placement usually does not matter. For our chi-square example, we're going to be using the carpool.jump data. This data shows how different things like sex, marital status, and other things affect the type of car an individual drives, for example. And our null hypothesis is that nothing affects the type of car an individual drives. In JMP, to conduct a chi-square test, just like ANOVA, we go to Analyze and fit Y by X. We would use the marital status as our Y and the type of car as our X. And since both are categorical, we're going to be getting a contingency. Click OK. As of right here, you can see the mosaic plot with single and married people and the type of car that they use, the family, sporty, or work car. And then as we scroll down, we can go and see the Pearson chi-squared value is less than 0.0001, which means that the marital status of individuals affect the type of car that they buy. Businesses can utilize this data to make more family cars or sporty cars where individuals are more likely to be married or single, for example, or in cities where there are a lot of individuals who work. For our third topic, we're going to be talking about control charts. For control charts, we have a lot of different types, but we will be focusing on 4 main control charts: the X-bar chart, the R chart, the S chart, and the MP chart. The X-bar chart is used to monitor the process using the means. So it makes sure that the process mean has not changed or shifted and that the process is in control. The R chart also used to monitor the process using the range, and it's usually accompanied by an X-bar chart. The S chart uses the standard deviation, and it's used instead of an R chart when the sample size is greater than 12 and less than 25. And the MP chart is used to monitor the number of non-conforming units. These charts make sure that the data and that our process is in control. However, there are still errors that can happen, like the alpha and beta errors. An alpha error is when the process that is in control produces a result outside the UCL and LCL. So we say that it's out of control, however, it is still in control. And the beta is when the process mean is still between the UCL and LCL, but the mean has shifted. For our control charts example, we're going to be using 2 data sets. The first data set used is airport.jump, which shows the delays at an airport in addition to the reason, date, and other stuff. And we're going to be using the X-bar and R chart for that. Here we can see the airport data. We have the day, the flight number, the delay, the reason, and the date. So to create an X and bar chart, X chart and R chart, we go to quality and process, control chart, and we go to X bar. This automatically also creates an R chart. So we go click on the delay, the process, and we want to group them by the date. So we use that as the sample label. As you can see here, this is our X chart. We have the mean as that, which is 9.53, our UCL, and our LCL. We have 4 points that go outside of the UCL and LCL, and they are grouped by day right here. For our second chart, the R of delay, we have 1, 2, 3, 4 points that are out of control. The reason for why these data points are out of control need to be identified and eliminated to make sure that there are no, or at least we can minimize the amount of data that's out of control as time goes on. For our second data set, we're going to use the data washers.jump. We're going to be creating an MP chart. So we go to Analyze, Quality and Process, Control Charts, and we click the MP chart. Here, the process, we use the defective column. We're going to sample label them by lot, and then we have to pick the sample size as our lot size. And then we click OK. And here we can see the number of defective items, and the average is 2.2. We have 2 points that are out of control in lot 4, and lot, it appears to be 9. The reasons these data points are out of control should be identified and fixed for the future. For our fourth topic, we're going to be talking about design of experiments. Simply put, they are experiments done to figure out what affects responses the most and how they affect them. Then, as requested by the user, experiments are designed to maximize, minimize, or match a certain target. Design of experiments consists of factors, responses, constraints, and sometimes a specific number of runs. How it is done? In JMP, a design is picked that I will show later, and then a table is created showing the different elements, and then after the tests are actually carried out, we put in the results. And the model used is a multi-regression model where we have many inputs and one output. Some designs models include a full factorial design, which is the most expensive since it tries every possible combination and it usually has 2 or more factors. A response surface design, which is usually chosen when we have a low amount of factors, usually between 2 and 8, and when we know the factors that are significant. A box spanking is a type of response surface design that doesn't require a lot of runs, so it is less expensive, and it usually requires 3 level factors. And then the screening design, which goes through many factors at once and fast to find the ones that affect the results the most. Basically, which ones are most significant. For our design of experiments example, we're going to use the popcorn DOE results. This data shows different factors, time, power, and brand, and how they affect the number popped and the total number of kernels. We want a combination of all factors that would maximize the number of kernels popped. In JMP, we're going to go to DOE and then click on Custom Design. And then here, we would create 2 responses, the number popped, and the goal is to maximize the total kernels, and we leave the goal as none. For our factors, we add the brand as a categorical 2-level factor with the values top secret and Wilbur, and then 2 continuous factors, time and power, with values 3, 5 for time and 5, 10 for power. And then we're going to define our constraints, which is the time and the power should be less than 13 and higher than 10. Then we would go and add the main effects, the interactions, we would click second, and then for the power, we would click second as well. Second. And then for the power, we click second as well. And then we would click here to make the design. And here we can see our anticipated responses. And then if we keep going down, we can actually make the table. Here, as you can see, we have the time and power, but we don't have the numbers popped and total kernels because we actually have to carry these tests out. Thankfully, JMP already provided a table that's already filled out for us right here with the number popped and the total kernels. So this is going to be a different design, which is a screening design, but we're going to run the script anyways. And we can see here that the time has a p-value that's less than 0.05, so it is significant. For our 5th and 6th topics, we're going to be talking about the linear regression and logistics regression. First off, linear regression is an approach used to model the relationship between variables linearly. The y value is usually dependent on the x values, and the response is continuous. Logistics regression is basically the same. However, the y value is going to be categorical. For our first example about the logistics regression, we're going to use the carpool.jump data. This data shows how different things like sex, marital status affect the type of car an individual drives. Multiple categorical factors will be used to show the relationship between these factors and the type. To create a logistics regression model, we go to Analyze, Fit Model. And then for the y value, we click the type. And as you can see here, JMP changed it to nominal logistic on its own. And then we're going to use the sex, the marital status, and the country as our factors. And then we click Run. Here we can see the model. We have the probability which is less than 0.0001. We have our parameter estimates here. And then if you go to the red arrow and you click the wall tests, we can see that the sex doesn't really affect the type of car individual drives, but the marital status and country affects it. However, the marital status affects it more than the country. And then for prediction, if we click the red arrow and then we click on Save Probability Formula, we get the required numbers to predict the type of car that an individual is going to drive. For our linear regression example, we're going to use the sample data bodyFat.jump. This data shows different factors of the body, so we're going to be using it to predict and show the relationship between different factors and the body fat percentage in the body. To create a linear regression model in JUMP, we go to Analyze, and then Fit Model, and then for our Y result, we're going to click on % body fat, and JUMP automatically changed it to standard least square, so it is not logistic. And then we're going to model the relationship between age all the way until hip circumference. We click Add right here. Then we run the model. As you can see here, the coefficient of determination, the R-square value, is 0.727236. And the closer it is to 1, the better our model is in predicting the body fat percentage. We can go down. We can see that the significant factors that affect the body fat percentage the most are the neck circumference, since the p-value is less than 0.05, and the abdomen circumference. And then if we go to the red arrow right here and click on Estimates and then Show Prediction Expression, and then go down, here we are shown the exact formula that is used to predict the body fat percentage. So if we multiply the age, weight, height, neck circumference by each of these values and then add them, we should get the expected body fat percentage, which completes our linear model. For topic number 7, we're going to be talking about reliability and survivability life distribution. It is a way in which we can analyze the lifespan of a product and fit it to a distribution. It can help us predict when a machine is going to break down, so we can plan accordingly, for example. The distributions that usually fit it are the Widball distribution, the exponential distribution, and normal distribution, and many others. For our life distribution example, we're going to be using the data fan.jump. This data shows the time taken for fans to fail. It will be done to predict when a specific fan might fail, and so that we can choose a specific distribution that fits the data. Next, for our example in JUMP, we would go to Analyze, and then Reliability and Survival, and click Life Distribution. For our time to event, we're going to click the time, and for our sensor, we're going to put the sensor column. As you can see here, we have the sensor code as censored, and we can change it to failed. However, we'll keep it as censored. And then we can have the confidence interval method, but we're going to keep it as default, which is walled. Click OK. And then we would go to our event plot. And here, the triangles show our censored data, and the X's show our failures for every fan. And then if we would go right here, we can fit the data into a distribution, and by doing a lot of things, but we can change the scale right here, and then we can fit to a log normal distribution or a Weibull distribution. The shaded part is the confidence interval, and then the better the distribution is, the better the data points will fall on the line it shows. And then if we keep going down, we can see some profilers, And then if we go up top, we can see the BIC right here. Next, we will be talking about the recurrence analysis. It analyzes a specific event occurrence over a span of time, in which a certain event can happen multiple times, hence the name recurrence analysis. It can help us show the expected cost of repairing a machine or the cost of continued treatment for a patient in the medical field. For our recurrence analysis example, we will use the data bladdercancer.jump. The data shows different factors that resulted in the death or survival of bladder cancer patients. The goal of the analysis is to obtain the mean cumulative function, which shows the total cost per unit as a function of time. Cost can be just the number of repairs, or it can be the actual cost of repair, or it can be the treatment or actual cost of treatment. In JUMP, we would go to Analyze, Reliability and Survival, Recurrence Analysis. For our Y, we would pick the age. For our label, we would pick the patient number. For our cost, we would pick the cost. And for our grouping, we're going to group them by treatment group. And then we click OK. Here we have the event plot with the dots showing the events. And then if we go down, we would get the mean cumulative function of the three drugs, which is the pyridoxine, the Hiotipa, and the placebo, which is basically no drug. And this is the cost over time through age. And we can also go individually to each drug and show the mean cumulative function, the standard deviation over age over time, the lower control limit, and the upper control limit. Next, we will be talking about the degradation analysis. What is it? It analyzes and projects failure data over time from historical figures and stats. The data does not actually fail, but it gets to a point where we consider it a failure. So let's say the data goes from 0 to 100. We would consider it a failure when it gets above 70. So it gets worse over time, hence the name degradation. For our degradation analysis example, we're going to be using the data gaslaser.jump. The data shows the increased intake of current by lasers over time. And when the intake goes over 10% for any laser, we consider that laser to be failing. In JUMP, to perform a degradation analysis, we would go to Analyze, Reliability and Survival, click Degradation, and then we would pick the current as our response, the unit as our label system ID, and the hours as our time. Then we click OK. Here we can see the overlay, and it shows us the degradation time for the currents, so the time for the laser's current to go up. So let's say for this specific label, or this specific laser, it would take around 3,500 hours for the current to go above 10%, so we would consider it a failure. And here we can go to the current transformation, and we can pick any other transformation other than the linear, which is exponential, square root, chi-squared. And then we would go down to see the current residual by hours. And then if we go up right here, and we click the Save Estimates, it would give us the slope and intercept, so we can have other data to show us when the lasers would go above 10%. So it's basically a function that would show us how different lasers would degrade over time. For our eighth topic, we're going to be talking about the time series. Time series is basically a number of measurements usually taken over a specific amount of time, or other stat like height, depth, temperature, etc. The interval between every measurement is typically the same. It is used for forecasting, and it utilizes past data for its predictions. For our time series example, we're going to be using the RaleighTemps.jump data. This data shows how the temperature varies over time. The intervals are exactly 1 month, and we're going to be using the Winters method as our forecasting method. In JUMP, we would go to Analyze, Modeling, and then go to Time Series. For our time series, we're going to be looking at the temperature, and for our time ID, we're going to click the month year, we're going to keep the forecast periods to 25 and the autocorrelation axis as 25. Then we click OK. Here, we can see how the temperature varies over the month, our mean, our standard deviation, and the number of periods, which is 131. Here we have the autocorrelation, which help us on deciding the moving average part, the partial correlation, which helps us on deciding the autoregressive part. The blue line is the confidence interval, which is 95% in our case. If the bar goes beyond the blue line, it means that the lag here is significant. And we use this to choose our autocorrelation model. If we continue on, for our forecasting prediction, we would go to the red arrow, click on smoothing model, and then we would go to the Winters method. And then we're going to keep the confidence interval at 0.95 and the periods per season to be 12. Then we estimate, and then if we go down, here we can see our forecasting for anything after the year 1990. The bottom and top blue line are the intervals, the upper and lower, and the red line is our predicted data. For our ninth topic, we're going to be talking about the Pareto plot. It is used to find out the most important factors among all the data, usually done to see the highest source of defects, for example. It contains both a histogram and a line, where the line represents the cumulative frequency, while the histogram shows the individual frequencies. The Pareto principle shows that 80% of our outputs come from 20% of our inputs. Or, for example, 80% of our profits come from 20% of our customers, if you want to put it that way. For our Pareto plot example, we will be using the data failure row data.jump. This data shows us various causes of failure for a specific system. To create a Pareto plot in JMP, we would go to Analyze, Quality and Process, and then click on the Pareto plot. We would use the failure as our Y. Then we click OK. Here we have the Pareto plot with the percentages of every failure showing with the histograms in descending order from highest to lowest, and the line showing our cumulative frequency. And as we can see here, contamination is the highest cause of failure. And if we go to the red arrow right here and we click on the show cumulative percent points, we can see the numbers exactly. So from 45 to 16 to 70 is basically showing us the cumulative frequency with contamination and oxide defect and so on. In a business, this can be done to identify which causes the most number of failures so we can fix it as time goes on. For our 10th and final topic, we will be talking about the graph builder. First of all, the box plot. A box plot is a graphical method of showing the data using its quartiles, the 25%, the mean, which is 50%, and the upper quartile, which is 75%. One of its advantages that it allows easy visualization of the max and min and the range, which makes it easy to compare different data sets which are next to each other. For our box plot example, we're going to be using the car physical data.jump. We will be using this data to show the different gas tank sizes for different types of cars. In JMP, we would go to Graph, and then Graph Builder. And then we're going to be using the type as our X, and then the gas tank size as our Y. As you can see here, we still do not have a box plot. So we go up here and pick the box plot. Here we can see the range, the upper quartile, the mean, the lower quartile. And you can see here data points that are out of the box plot. These are usually called the outliers. Also, if you go here, you can change the box style from outlier to solid, thin, or quantile, as you can see here. So it extends the box. Next, we're going to be talking about the mosaic plot, which is a graphical method of showing two or more categorical data sets. When the data we are comparing is categorical, we use the mosaic plot. It also makes it easy to identify different relationships between the data. For our example, we're going to be using the Titanic passengers.jump data. The mosaic plot will be used to show the amount of people who survived depending on their class. To create a mosaic plot, we will go to Graph Builder, and then we're going to be looking at if passengers survived depending on their class. And then to click the mosaic plot, we'd go all the way to the right up here. And here we have the mosaic plot. So from the mosaic plot, we can see that if your class was number 3, you probably would not survive, or chances of survival are not as high as a passenger who was in the class number 1. This can be used in businesses to see the different relationships between data easily. Next, we're going to be talking about the line chart, which is a graphical method of showing data as a series over time connected by a line. It is used to visualize a trend in the data. For our example, we're going to be using the smartphone OS.jump data. The line chart will be used to show the variability of the market share of different operating systems over time. To create a line chart in SAS JMP, we would go to Graph and then Graph Builder. We would use the year as our X, the market share as our Y, and then we want to group them by the operating system right here. So from the year 2006 to this year right here, for this operating system in particular, the market share goes from around 26% to 3% in 2011, and so on. In businesses, this would allow us to do a lot of things, like see the trend and plan accordingly. This concludes our presentation for today. I am Yazan Shnudi. Thank you so much for listening.